Hi everyone, this is a video response for some homework questions that were requested by students. What we're going to do is do question 3 from the 6.4 handout I gave you. The answer key is already in Brightspace, but this video is going to try to go through this one step at a time. I also have a request for question 14 from page 344, that is 6.4. It's very similar to what we're doing, but there is a little twist. I could consider this like a semi-thinking, a heavy application or a semi-thinking question for you. And then lastly, I decided to throw in a question of my own, which gets you to practice a ramp style question with a twist. So I just made that up. Okay? There's a little bit more because I'm adding force friction and trying to twist things around. Let's see how we go. Question 1, or rather, question 3 from 6.4, the handout. Biff wishes to fly 508 kilometers from Toronto, I pre-drew, to Montreal. It has a bearing of 78 degrees. Great. The airplane in the air, not with respect to the Earth, just on its own, can travel at a top speed of 550 kilometers. An 80-kilometer wind right now is blowing on a bearing of 125. By 125, I'm going to say it's about here. Okay, so this is wind, and it has a magnitude of 80 kilometers an hour, and this is going to be 125 degrees, but we know the 90 degree is right here, so the angle from the horizontal to the vector is 35 degrees. Okay, let's do it. The question says, in what direction should the pilot fly to reach the destination? It implies you've done a lot of questions like this already. What we want is from Toronto to Montreal to be my resultant. What does that mean, and why do they ask for in what direction should the pilot fly? You might be thinking, can't you just fly at a bearing of 78? No, the question told you that there is a wind velocity. So if I want my Toronto to Montreal to be my resultant, as in this is where I start and this is where I end up, I need to fly my plane in a slightly different direction so that it accounts for the wind and it pushes me to the direction I want. So the plane is going to fly in an unusual direction, actually north of Montreal, but the wind of 80 kilometers an hour is going to push me back down, which will allow me to arrive in Montreal as if I was flying a straight line. That's the question. And this is the triangle. So let's take a look. What am I going to use? Well, since I am looking for the direction the pilot should fly, because this gives me a speed, I'm assuming that I use the speed here and I use the speed here for my benefit. I actually can't use 508 right now. Why? Because when we're using things like sine law and cosine law, the units or the magnitudes that I'm using, they have to agree the nature in which they describe. If it's a kilometer per hour, then the other number should be kilometer per hour. If this is like meters, then that should be meters. The units need to agree. So since 508 kilometers is a distance, I'm going to sort of put that off on the side. I can see I have two numbers here, so I'm going to predict those are the numbers I will probably have to use for my calculations. So let's get to this. Okay, I have two sides. So I could have side angle side. It would be great if I have this angle. I could use side side angle. It would be great if I have this angle. Any of these angles that I get, I can use to my advantage, and I'll use either sine law or cosine law depending on what's in front of me. So let's try to fill it in. You know that this wind angle of velocity, which is right here, has a 35 degree south of the horizontal, which means this is 35 degrees, which means this half or this portion of the top corner angle is going to be 55. Unfortunately, I don't know what that is. Okay, I have no information. The 78 is not being divided by 2. I don't know. I'm just going to leave that as theta or something. Let's see, what else do I know? If this is 55, then my horizontal, a piece of this right corner is going to be 35 degrees, right? Or another way you can say is PLTZ, parallel line theorem. I know that this is going to be 35. And take a look. The vector from Toronto to Montreal has a bearing of 78, which means the angle to the horizontal is going to be 12 degrees. PLTZ once again, right? PLTZ once again. The lower part of this corner has an angle of 12. The total angle of this corner M is 47. So look, I have side, angle. I can use sine law. Let's try it. Side to angle, which will help me get this angle, and I can answer what the direction of the pilot is. Here we go. Part A. Sine of 47 degrees all over 550 kilometers per hour is equal to sine of, let's call this theta, over 80 kilometers an hour. So sine theta, if I were to do some algebra, multiply both sides by 80, I have 80 times sine 47 all over 550. So excuse me while I cheat and look at my answer key because I don't have a calculator on me. It seems I am going to have my angle to be approximately 6.1 degrees. So this is 6.1 degrees. The picture is not the most to scale, obviously, but that's okay. If I know, let me simplify this. I have a triangle here, and I know that this is 12, and I know that this is 6.1. What is the bearing that my plane has to go so that with the wind I reach Montreal? Well, I'm going to say the bearing will be 90 degrees minus the 6.1 degrees minus the 12 degrees. Because these three angles are complementary. We have 978, 71.9 degrees. Hope I'm doing that right. Let's take a look. 71.9 degrees. Great. So in what direction should the pilot fly to reach the destination? You could say a bearing of 71.9 degrees, or you can say north 71.9 east. Either one is okay. Okay, so at what speed will the plane be traveling? Careful, this is actually relative to the ground. Why do I say that? We already know what the airplane can travel at. However, the question is asking, how fast is the airplane traveling from here to here? AKA, what is the magnitude of this resultant if the plane can travel this fast while the wind pushes it this fast, right? So if I look at the y vectors, the plane is traveling this way, but the wind is pushing it back that way. So it's resisting. However, if you look at the x vectors, the plane is traveling this way, and the wind is also pushing it this way, which means it's actually traveling this way faster. You might be surprised at what the resultant vector might be. So let's do it. What is the magnitude of r? The magnitude of r, I could calculate this with, let's do sine law. Let's continue with sine law. I have sine of 47 degrees to 550 is equal to sine of, I didn't figure it out yet, over the magnitude of r. What do I mean by I didn't figure it out yet? I actually don't know what the opposite angle of magnitude r is. Okay, and so let me do that very quickly. Sorry about that. So 180 is the total of a triangle, subtracted by 47 degrees because that's the M corner, subtracted by 6.1 degrees, which is the sliver corner right here, which leaves me with 180, 133, 1, 2, 7, 6.9. Oh my gosh, that's just quick mental math. Let me see. That's very tiring. 126.9. Okay, so I'm not crazy. 126.9. So if I plug in 126.9 degrees, I should be able to simplify and figure out what the magnitude of the resultant vector is. And of course, because I'm using speed, the resultant magnitude will also be the speed. The final answer when you simplify should be 601.4 kilometers per hour. Okay, so that is the overall speed of the plane with the wind helping it. Part C says, how long will the trip take? Well, you know that speed is always distance over time, or velocity equals displacement over time. And so time is going to be displacement over velocity, which is equal to a distance of 508 kilometers divided by 601.4 kilometers per hour. Time will give you approximately 0.84 hours. That's it. Okay. Again, it's not particularly different from all the other questions you've done. You know what resultant is. You know that you have to use sine law, cosine law given the angles. But here, the difference is I'm giving you the answer, aka I'm sort of giving you the resultant, and I'm asking what the components or the sum, the vectors are. Here's another one. So this one was from the textbook, as I said, from 6.4. It has another twist. Here we go. Andrea flies planes that drop water on forest fires. The forest fire is 500 kilometers away at a bearing of 230. Okay, so how will we try to make sense of this? Two lines. A bearing of 230 is 50 degrees in the into the third quadrant. So if I am here, or Andrea is here, the fire is going to be maybe somewhere there. I have this bearing to be 50 degrees, and this distance is 500 kilometers. And here is a fire. Okay, that's the best I got. Okay. A 72 kilometer per hour wind is blowing from a bearing of 182. 182 is also in the third quadrant. So you would think I'm drawing an arrow like this, but that's actually not true. Please take a look at this keyword. It's coming from here. In other words, my arrow is pointing the other way. Wind is actually blowing that way at an angle of 2. In other words, the angle from the horizontal will be 88 degrees. Think about that one more time. A wind is blowing from a bearing of 182. So if it's blowing from, cross the origin, it continues on in this direction, not the southern direction. That's the trick. Please be careful. Determine the heading that Andrea should set if the airplane will be flying at some kilometers per hour. Okay, so we have 72 kilometers per hour wind. Let's call that wind. This is where I want to be. And so my plane has to go from head to tail there. So my, this is my plane. and I don't know. It says, so part A, it's going to be 230 kilometers per hour. I need to figure out what the heading is. I need to figure out the bearing of P. So there's my triangle. Let's do it. Let's add some degrees or add some angles inside the triangle so that I can start using either sine law or cosine law or whatever. Let's see. Since I know what do I know? My goodness. So since this is 50, I know the inside here is 40. I know that's a 90, and I know this part slightly to the right of the north direction is 2 degrees, which means this entire angle is 40, 90, and 2, 132 degrees. Okay, do I have any others? I suppose I could figure out this angle and this angle, but I can't say that will help me. In fact, I think that's all I need. I have one angle, I have an adjacent side speed, and I have the next adjacent side speed. I have side angle. I can use sine law again. So let's try it. If I use sine law, I can figure out the angle inside here and the angle inside here. I think this will help me a lot because I know what this angle is to the south, which means I can just subtract that. Yeah, I think we got it. Here we go. I am aiming for this angle, so how about we call this theta and alpha. Okay, a sine of 132 degrees is paired up with the side 230 kilometers an hour. It's getting a little fuzzy, so let me rewrite that a little more clear. Okay. Sine of 132 degrees is over 230. And that is the same ratio as sine of some angle over 72 kilometers per hour. So this angle to 72, which is equal to sine of alpha over the resultant speed. Although I don't know what this is, I don't know what that is, I don't know what that is, I can figure that out. Let's start with that. By algebra, sine theta is going to be 72 sine 132 divided by 230, which is equal to something. I'm going to do all of that in one go and calculate the angle itself. I don't have an answer key, so bear with me. I need to type this up. Get out my calculator. 72 sine 132 divided by 230. Inverse sine that, and the angle becomes 13 point, I'm going to round, 13.5 degrees. Okay, that means angle alpha being a total interior angle of a triangle minus 132 degrees minus 13.5 degrees. We have 4.5 degrees. Okay, so as I said, let's zoom in on that top corner. I have an arrow here, I have an arrow there, right? And this is an angle of 34.5 degrees. What's interesting though, my angle from the south, this part right here, is the same as that little sliver we talked about by PLTZ. That is 2 degrees. And so if I were to say from the south, my bearing of this vector is going to be 2 degrees plus 34.5 degrees. The bearing that the plane has to fly, I'm going to say the heading of the plane is 36.5 degrees from the south. 36.5 degrees west. This question will completely change in number if the number I used here was 300 kilometers. You will see that if this is in fact 300 kilometers, this vector should be represented to be much faster, which means that vector will be significantly, it will affect the resultant a little less than before. Okay, so try it again on your own. This should be 300, which will change this angle, which in turn will change the angle. Your 2 degrees will not change, obviously, and so you should get the final answer and check the back of the textbook. Explain the difference in results. Well, I'll leave that to you. The hint is what I just talked about and how it makes things different. Okay. Hope that's enough of an explanation. I'm going to wrap up this video by answering the very last question I created. So if you want to pause this right now and give it a try yourself, by all means go for it. Here's the explanation. A 5 kilogram crate sitting on a ramp, incline is 15 degrees above the horizontal. There is a rope and it is pulling upwards on the ramp, pulling the crate up the ramp, but a friction force is resisting it. If the crate is just about to start moving uphill, that's another way of saying everything right now is in perfect equilibrium. What is the tension force? That's the question. So let's add a couple more vectors to showcase what's exactly happening on the crate. The crate is 5 kilograms, so that implies immediately that we have a force of gravity of m times g, which is 5 times 9.8. I'm gonna round it to one decimal place. 5 times 9.8 is 49 newtons. Of course, it's down. Okay. This, however, can be broken down into its components, and I am going to declare that my, let's just say my reference for my x is going to be the ramp's incline, and so my y component is going to be perpendicular to the ramp surface. If force of gravity is pushing it this way, that means there should be some kind of force making the crate fall downwards, and also some kind of force pushing directly perpendicularly into the ramp. Right? At the same time, there is a friction force that is pushing it this way by 30 newtons, because it says it's resisting the pull, right? And because I see something going left, I'm assuming the 0 vector is caused by the tension pulling right, which leaves me with this vector not balanced. That down vector perpendicularly going into the ramp will be balanced by a normal force pushing up perpendicularly so that it is just sitting there at rest. If I were to turn this into a vector diagram, I would have something like, let's see, the force of gravity, but the x component this way. The force of gravity, plus the tension, let's call that 30 newtons. The friction, let's call that 30 newtons. I have the force of gravity going in the y direction, the y component. I have my tension then, bringing it all the way back up. to this point, and then my normal force balancing out that y component of the force of gravity, bringing us back to rest. This is my situation. So take a look at my vector diagram. If I have this, canceling out that, all I really have to do is figure out what this is to tell me what the magnitude of my tension is. That's it. So the twist in this story is you have to know the force of friction and the force of gravity's x component sort of add together to balance out the tension, because the question says it's just about ready to move. So let's do it. This question, if you don't know how to draw the graph or draw the diagram, is the hardest part. But if you do, you know that the magnitude of the force of gravity in the x direction, so the x component, is going to be the magnitude of the force of gravity multiplied by, let's see, let's call this my angle. It's going to be adjacent, so cosine of theta. Now, it would be great if I knew what that angle was. Force of gravity is 49 newtons. The theta is going to be the complementary to 15 degrees. How do I know that? Consider this. If I have a right angle triangle with 15, that's a 90. And so what's this angle? 90 minus 15, 75. That angle is the same as this angle created with the x and the vertically down. Together, the magnitude is going to be 49 cosine 75, approximately 12.7 newtons in the negative x direction. So the magnitude of the tension is the same as 30 newtons plus 12.7 equals 42.7 newtons. My tension is 42.7 newtons to the right, or I guess up ramp is the best way to describe it. There is no northeast, southwest in this situation. Hope that clarified a couple of things or gave you some, I guess, encouragement or confidence in knowing that what you're doing is correct. Hope this was helpful. Let me know through email what else you might want to review before the weekend is over. Come on Monday with lots of questions, and I'll see you then. Have a good weekend.